Okay, so yesterday we looked at momentum. Very difficult understanding.
You know, real brain hurt right there.
Okay, so today we're just going to take this idea one step further, right? Just one step first. Okay, and we're going to look at what happens when two things collide.
Impulse.
So not impulse. Impulse is change in momentum, usually for a single body, as the momentum of an object changes with time. So if you think about something, if you have constant velocities, you have constant momentum because it is mass times velocity. But do we always have constant velocity? No, we could have constant or complete change in velocity every single second. Right? So if you are under acceleration, your velocity is changing all the time, which means that your momentum is changing all the time. And so if you wanted to look at your instantaneous momentum, that's what we call your impulse. Okay? But we're not looking at that. We're going to actually look at collisions and the conservation of momentum, right? The principle behind conserving momentum. So during an impact, when two bodies collide, there is a transfer of momentum. So one of the easiest examples to think about is if you hit a nail with a hammer. You hit the nail, right? What happens to the nail? It sort of moves a little bit down into whatever you're hitting. What happens to the hammer? It rebounds, doesn't it? You get that ding as it bounces off, right? Think about a ball bouncing off the wall. Right? There's a bit of transfer of momentum there as well. Okay, so when two bodies collide, there is this transfer of momentum. So some momentum, right, not force, momentum is transferred from the first object to the second object. But what did Newton say? For every action, there's a reaction. So there will also be some transfer of momentum from the second to the first. Okay? So because impacts happen so quickly, we don't have to consider other forces in the impact. In other words, we're not going to consider friction in the impact because an impact happens like that. Right? So it's not like an impact happens at its place and time, but it happens immediately. And we consider the impact instantaneously. And so because of that, we don't have to worry about other external forces like friction, air resistance, and so on. Right, so the change in momentum caused is normally due to the contact forces between the objects. Now, we've learned about normal contact force. If you're standing on the ground, you're putting weight on the ground, and the ground is weight on you. When two objects collide, there's a transfer of contact force. One object is forcing the object in one direction, and the other object is forcing the object in the opposite direction. And because these forces are equal and opposite, they end up cancelling each other out. Okay, so the only forces we need to consider, right, if you have a look at my little blue and green block or red blocky over there, are the normal contact forces. So I haven't technically drawn the diagrams accurately. These forces need to be acting in the opposite. We don't draw them like this, right? But I want you to consider the blue block is exerting a force on the red block. So actually the red block is receiving that force. It's going in the opposite direction. And the red block is doing exactly the same thing to the blue block when they collide. Now, as stated before, because we have Newton's third law, because he decided to make that up, he was just like, I can't work this out, so they must be the same. But obviously it's been proved, right? So because these forces are equal and opposite, they cancel out. This means that the momentum transfer from the first object to the second object is exactly the same as the momentum transfer from the second object to the first object. And that is really lovely.
Yeah.
Why is that really lovely?
Because that makes our lives so much easier.
Right? It means that the total momentum before and after must be the same. Okay? And I'm sure you've seen this lovely diagram many times before. You see how there is a lovely explosion there. It's for you, Kiana, the explosion.
Where's that from?
I don't know. I just
Georgia.
okay. So this brings us to the conservation of momentum. Total momentum is conserved in an impact. In reality, is it really conserved? In the real world? No. But when we take our modeling assumptions into account, we are saying that the transfer of momentum, the loss that we have is so little, we'll just assume it's exactly the same. And in the real world, obviously, it doesn't work.
So that's how these things work.
Yeah, there's actually that tick-tock, there's instantaneous change in momentum from one to the next, to the next, to the next. And the only one without resistance is the one on the opposite end. So it goes up, and then it comes back down. You don't obviously see the transfer of momentum between all the balls, but it's happening in an instant. Right? Now, theoretically, if there was no loss of momentum, what would that thing continue doing? It would continue forever. But does it continue forever? No, there is a little bit of loss of momentum. Right? Because there's air resistance, there's actually friction. So there's many forces at play. But when we model them, we take away those assumptions.
We put them in a perfect world.
Yeah, we put them in a perfect world. Okay? So just quickly, if we consider the momentum before, right? If we have two objects traveling, now these objects can be traveling in the same direction, right? What direction are my objects traveling? I have a look at my vectors. Which way are my vectors pointing? They're both pointing in the same direction. So in my modeling assumption, I'm saying that these objects are traveling in the same direction. If they weren't, what would I do with my vectors? I would change them around. If I consider the vectors then of objects traveling in a different direction, what do they become? Negative, right? Remember that. Okay, so after they explode, the momentum, right, the total momentum. So when we consider total momentum, what we're saying is if we take the two objects and we add their momentums together, before they collide and after they collide, they must be the same. Because we're saying we don't lose momentum, it's conserved. Now this is very lovely because, and I'm sure you've seen those formulas before, m1u1 plus m2u2 equals m1v1 plus m2v2. In other words, that's just initial velocity, right, at the instant of impact, and the velocity directly after impact. So we aren't really considering how the object got to that point. We're just saying, okay, at that very moment that they hit, u is the initial velocity. So u is impact velocity, and v is immediately after what happened. So here we get to our very first example. So we have two balls, two ball bearings to be honest. They are moving directly towards one another. So that's why in my vector diagram, I have my arrows pointing towards. Who decides in which direction is positive? I can decide, okay? Except then I need to consider anything that is not pointing in the direction that's positive to be negative, okay? So after the collision, before the collision, one of the balls is traveling at 3 meters per second. One of them is traveling at 1 meter per second. After the first collision, we'll see that the first ball bearing is traveling 0 meters per second. And they want us to find the speed of the second ball. After these two objects impact, do I know in which direction that other ball is going to travel?
No.
I don't actually know. But what's going to tell me?
The direction.
The sign of whatever I get out. Okay? If it's a positive sign, it means that it's going in the direction that I chose to be positive. If it's negative, it means it's going in the opposite direction. So you'll see on my diagram, I've just put a question mark. I can make an assumption, but I might be wrong, and I just need to remember that. Okay, so you need to consider what comes out the other side. So I will not bore you with too many details, but let's have a look at how we've calculated this. Okay, we have to first consider the total momentum before. And to consider the total momentum before, we're just going to add all the momentums together. So if momentum is equal to mass times velocity, here's the mass of the first object, right? Remember, I had to convert, it's in grams, I need to convert to kilograms. We don't measure momentum in grams. Okay, and the speed was 3 meters per second. Now I'm going to add the momentum of the second object. The second object's velocity, what is it? If it's traveling towards the first object, and I've said the first object's direction is positive, what is the second object's direction? Negative. So that's why we have -1 over here. Right? So let's look at the diagram. It's very important for momentum, right? You don't want to consider the velocities to both be positive, right? Because remember, momentum is a vector quantity. It has direction. So here we have the -1 from our red ball. Right. Simple calculation, we will get total momentum of 0.035 meters per second. That's how much total momentum these two objects have at the instant just before they go to impact. Okay, they are traveling towards each other. So they're going to go for boom, like such. See, boom. And after, something's going to happen. Now the question is going to tell you what happens. We're going to learn there's 3 scenarios that can happen. One is that one is going to stop and the other one's going to continue. The other one is where they're going to hold hands. The other one's where they're going to explode. So in the example here, we are considering now the first object has stopped. So its velocity is what, right? Something is not moving, it has 0 velocity. So we're going to calculate the total momentum for this second scenario. We have 0 velocity times its weight, which means its momentum is 0. And the second object, we've taken its weight. Were we told its velocity? No, so we'll just leave it as a variable, right? And then we will just remember that the total momentum before and the total momentum after must be the same. And so I calculated the total momentum before, which means the total momentum after must also be there. And so I can solve for the final velocity. I get a velocity of 1.4 meters per second. So in which direction was the second ball now traveling? In the positive direction. Who set the positive direction? I did, right? I could have changed this problem and I could have pointed the arrow in the opposite direction. What velocity would I have got there? I would have got a negative velocity, and that would have told me this ended up going away from where I thought it was going. Okay? So again, don't get confused with minus signs. Minus signs just mean that maybe you've made the wrong assumption, right? Or the object is actually traveling in a direction other than positive. Right. Sometimes objects, right? Come on, Zara, whip out the English. What does the word say? Coalesce. Okay. So when objects coalesce, right? So we have 2 objects that collide. They go boom. And instead of one stopping and the other one carrying on, they join. So they become one object, right? And they move together. So there's many examples of this. If you jump onto a running train, if 2 people are ice skating and they suddenly join hands, right? They coalesce, they join together, right? And when they join together, we can consider them as one object. We can combine their masses. So they have a combined mass, which means that they have a combined momentum. Okay? The opposite is an explosion. Right? This is when you have an object and the 2 masses separate from each other. So if you jump off the back of a bucket, is a good example. Right? While you are together, you have combined momentum. If you jump off, your momentums will separate. Make sense? Okay. And when we consider things that explode, we just need to remember that we need to know that the individual masses of each object. So we could have a combined mass to begin with, and then it could separate. Or we could have a separate and it could combine. Fortunately, we don't really go into more detail than this one. Okay, Bob's back. Just for you.
Oh, Junior.
There's Junior, okay? This is Bob's sister, Bobette.
Okay.
Okay?
What is he when he's dating his sister?
Okay?
That's okay.
Oh, we've got a bit of family insisting. Okay, fine. Okay, so here we go. Okay, so we have a girl sitting on a sled. Okay, so there's Bobette on the sled. Right, they have a combined mass of 50 kilograms. So because she's on the sled, we can consider it as one object. Okay? So it will have a single momentum. Right, when the girl and the sled are moving at 2 meters per second, there's another girl. Okay, so there's Bobette and Bobette Senior maybe, right? She throws a snowball at the sled.
No, that's Bobette's younger sister.
Younger sister.
Younger sister.
Okay, so here we have this snowball. Before impact, these two objects are separate, which means that they each have their own momentum, right? Now, the snowball is coming towards you, so the direction must be opposite. Okay, it must be in the opposite direction. So what they want us to find is find the speed of the sled after the impact, right? Now, this is a 200-gram snowball. I want you to think about a 200-gram snowball. I think
The other sister's heavier than the older.
maybe
No,
the snowball is 200.
No, I know. But look at the weight of the system.
Okay, so what we've done is when we draw a picture, we're going to consider the mass of Bobette and the sled together and the snowball separately. And after they collide, we are going to say they coalesce. In other words, they are joined. And what do we do with the masses when they are combined? We add them together. We could consider them separately, but we don't need to. That's why we combine them. Okay? So, mind-numbingly boring equations. We take the total momentum. The only thing you have to be careful with is the velocity. You can't forget that velocity has direction. It's very easy to think, why am I taking the momentum of something as negative when it's traveling towards something? But that doesn't make sense. It's just because it's going in the opposite direction. Yeah? So we have to consider this momentum to be negative here. Right, that gives us a total momentum of 97.89 newton seconds. Okay. These objects coalesce. If you see the word coalesce, it implies that there's been a conservation of momentum and that the two objects have joined forces. So I don't think that snowball is sitting nicely next to Bobette on the feet. It's probably sitting in her face. As was intended. Okay. So after the collision, we have the momentum equal to the combined weight times some velocity. Okay. And we can even state, right, that this combined velocity, this combined momentum must equal 97.89. And the reason for that is because momentum is conserved in an ideal world. Okay? And obviously we can solve the velocity. 1.95 meters per second. Which direction is the sled traveling? In the direction we define as positive. Okay? That's the simple reality. Okay, now we have some blocks. So in the first example, we have the two blocks moving in the same direction, but because the first block is moving faster, it's going to catch up to the second block. I'd imagine being in a car and a truck drives from behind you and decides to join forces with you, and you become one.
That's not a good idea.
No.
No,
Okay.
no.
Now, you don't have to be elaborate and draw fancy diagrams like this. They can just be very simple, but it always helps to draw a picture of what's going on and look for the keywords. So we have a block of 0.2 kilograms because I've converted from grams to kilograms, right? And it's traveling at 4 meters per second. And draw arrows for your vectors, guys, so you can see in which direction that they go. So you don't forget what must be positive and negative. Because sometimes if we have a look at the second example, we have no negative vectors because we are saying these objects are moving in the same direction. So if we consider the first where they are moving towards each other, the second block has what kind of velocity then? It will have this block's velocity. What would you say about this block's velocity when we're calculating momentum? Well, have a look at going to be negative.
Negative, right?
Okay, well, you could make it positive, but then you'd have to make the other one negative. So if I set my direction of motion quickly, let's say that's the direction of motion, anything going in that direction has a positive velocity. Anything going in the opposite direction has a negative velocity. And because momentum is calculated on velocity, it will have a negative momentum. Okay, that doesn't mean it has negative momentum. It just means it has negative momentum going in the opposite direction. Right, that's all plus and minus mean in the vector is direction, not magnitude. Don't think about because it's a minus number, therefore it must be smaller. Okay? That's got nothing to do with it. It's the direction. Okay, so if we consider the direction of the first block, then we consider the direction of the second block. If we combine their momentum together, we get 0.3 newtons. One is positive, one is negative because it's going in the opposite direction. When we add them together, that's their combined. Right, once they collide, they've told us that these two objects end up moving together. Do I know the direction in which they are going to move? No, right? If you didn't know, you looked at the two boxes, the first two boxes. The one is small and the one is big. Maybe that second box is big and going fast enough to cause both boxes to move in its direction. Or maybe the small box has got enough momentum to get the big box to change direction. Okay? Think about a tugboat and a super tanker. You might not know which direction when they collide, which one's going to go in what direction. Maybe that tugboat's like ate its spinach and.
Well, I mean, tugboats.
Wait, what's the company?
Popeye.
Popeye, yeah.
I mean, tugboats are built not to have a lot of speed, but to have fun now.
There we go.
Hence,
Same thing, a bullet and a supertanker might have the same momentum. One has big momentum because of velocity, the other one has big because of mass. Okay? And so we can't always assume and say it's going to happen in a. But the nothing thing is, if you consider your vectors correctly, your answer will tell you in which direction they go. Okay? And so I end up with a positive answer, and that tells me that they both traveled in the direction I assumed as positive, which was, well, in my example, from left to right. Right, after, in the second example, both these objects are moving in the same direction. Now, if the second object was behind the first object, would they ever collide? No, because the one is going again faster than the other one and they'd never catch up. Okay, so you have to use a little bit of common sense when you draw these. Okay, if something is moving in the same direction and they're going to collide, the faster one needs to be behind. Okay, so here we have the small box at 4 meters per second, except this time instead of traveling towards the small box, the big box is traveling in the same direction. And that's why my vector is now pointing in the same direction. So what kind of momentum will it have this time? So positive or negative? Also positive, because they're both traveling in the same direction. Okay. So if we consider their combined momentum, that's where we get that 1.3 seconds. And because we can consider their weights together, we don't have to consider them separately. And we can calculate the velocity as 1.86 meters per second. In which direction are they going? In the same direction. Okay. I would be very worried if you got a negative answer here. When two objects traveling in one direction collide and sort of go in the opposite direction, that would be a new thing. A new thing. Okay, well, I wish I could say that there's anything else interesting to learn about that, but
Oh, wow.
that's as far as we go into the momentum rabbit hole. We don't go any deeper than that. We don't even we don't consider impulse, which is sad because impulse is so fun. But that's it. That's all you need to know about momentum is how to calculate it and conservation of momentum. That momentum before and after is the same. And that's it.